Chapter 1.7 Transformations of Functions. In this chapter, we are going to be taking a bunch of different parent functions, and you'll know what a parent function is in just a sec, and we will be transforming them. That means we are going to be shifting them up, down, left, right. We will also be stretching them vertically and horizontally and shrinking them vertically and horizontally, changing the shape of the individual functions themselves. So here is a list of 8 different parent functions that you guys should be familiar with, right? Again, a parent function is simply the most basic form of a particular type of function, right? First off, we have constant function. The constant function f of x equals c. Every constant function is just going to be a horizontal line. We have our identity function. F of x is equal to x, y equals x. That's a line with a slope of 1. We have our absolute value functions. Notice the absolute value function forms a v. We have our square root functions. Square root functions, I like to call this the swim move function. It looks like an arm is coming up out of the water to make a swim stroke. We have our quadratic functions, and as you guys know, every quadratic function has the shape of a parabola, this nice U. All right. We have our cubic functions. I like to call this the monkey man. It looks like some monkey arms going up and down. All right. We have our reciprocal functions and our greatest integer functions. Now, there are 4 here that we are going to focus on in this particular section, and that is going to be your absolute value functions, your square root functions, quadratic functions, and cubic functions. The important thing to recognize is that every single absolute value function is going to have some sort of V shape or upside down V. Every single square root function is going to have this swim move type of shape to it. Every single quadratic is going to have a parabola shape, and every single cubic function is going to have these monkey arms. Okay, all right, and so again, these are called parent functions because they are the most simple form of a particular type of function. What we're going to be doing now is taking all of these functions, all right, and transforming them. All right, now again, we have these reciprocal functions, greatest integer functions. These are much less common. We won't be dealing with these here in precalculus. You might see reciprocals more later on in the year or in calculus next year. Greatest integer functions, rarely see those. I'm confident that you guys are comfortable with constant functions and identity functions. That would just be lines, right? So in this case, we will not be dealing with those 2 either, all right? The main ones, absolute value, square root, quadratic, and cubic functions. So let's talk about our transformations. It says, given a parent function f of x, the function g of x is equal to f of x plus d has a vertical shift of d units. In other words, if I have a function g of x, and that function is equal to my original function, the parent function f of x, and I am adding some constant outside of that parent function, whatever the value of d is will determine my vertical shift. All right? For example, identify the parent function and any transformations. Sketch the graph. Here we have the function g of x is equal to x squared plus 2. Well, when you guys see the word parent function, again, all we are talking about is classifying the type of function. What is the most simple form of this particular type of function? Well, this function is a quadratic function, and the most simple form of a quadratic function is going to be f of x is equal to x squared, or y is equal to x squared. That is the most simple form of the function that g of x is related to. So now we have to describe the transformations. What is being changed? Well, notice that g of x has a plus 2 on the outside of our parent function. I'm taking the parent function x squared, and I'm adding 2 on the outside. Adding a number outside of the parent function creates a vertical shift of d units. In this case, by identifying the constant d, which is 2, we can tell that this is going to have a vertical shift up of 2 units. Notice, if we were to graph the function f of x is equal to x squared, this is our parent function. Again, you guys know the shape of this function. It is a parabola. To get to my function g of x, I am going to take every single point that is on my parent function f of x and shift it up 2 units. Shifting every single point up 2 units will give me my function g of x. Notice the vertex of this parabola that was originally at 0, 0 moves up to 0, 2. Okay, this point that was right here, this was the ordered pair 2, 4, moves up to 2, 6. Every single point on the parent function shifts up 2 units. Let's take a look at another example. Identify the parent and any transformation. Sketch the graph. G of x is equal to the square root of x minus 5. Well, what type of function is this? What can we classify it as? This would be a square root function. Our parent function is f of x is equal to the square root of x. What's different from our parent function? Well, we are subtracting 5 on the outside of the parent function. Notice root x is the parent function, and then I am subtracting 5. What is our value of d? Well, if I am subtracting 5 outside of the parent function, that means d is going to be equal, this constant d is going to equal negative 5, and d controls our vertical shift. In this case, because d is negative, that means every single point is going to get shifted down 5 units. So here is the shape of our parent function. Here's the graph of f of x equals the square root of x. And what is going to happen to every single point on this graph? It is going to get shifted down 5 units, giving us our function g of x. Notice this point that was originally at the origin 0, 0 gets bumped down to 0, negative 5. Similarly, we had this ordered pair 4, 2. We have now the ordered pair 4, negative 3. Every single ordered pair on our graph of f of x gets shifted down 5 units to give us the graph of g of x. That is our vertical shift. Okay, so identifying the constant d will give us our vertical shift. We also have horizontal shifts. Given a parent function f of x, the function g of x equals f of x minus b has a horizontal shift of b units. Notice that a horizontal shift occurs when we subtract a constant inside of the parent function. Okay, we are subtracting a constant b inside of the parent function. For example, identify the parent and any transformations, sketch the graph. Here, what type of function are we dealing with? Well, this is a cubic function. What's the most basic form of a cubic function? F of x is equal to x cubed. That is our parent. What's different from the parent to get to our function g? Well, we are adding 4 inside of the parent function. Notice that it is inside of the parentheses. This would be evaluating f of x plus 4. Right? We're plugging in x plus 4 where we would see an x. Well, what does that mean for our constant b? Remember, this is f of x minus b. In this particular case, to get a plus 4, that would mean that b has to be a negative 4. B tells us what our horizontal shift is, and because b is negative, that means we are going to have a horizontal shift to the left of 4. So here is the graph of our parent function, y equals x cubed. How are we going to get the graph of g of x? Well, every single point on our parent function is going to get shifted to the left 4 units. That horizontal shift of left 4 units brings us to the function g of x is equal to x plus 4 raised to the 3rd power. Let's look at another example of a horizontal shift here. Identify the parent and any transformations. Sketch the graph. So here we have g of x is equal to the absolute value of x minus 3. What type of function are we dealing with? Well, this is an absolute value function. The most simple form of an absolute value function is f of x is equal to the absolute value of x. What's different from the parent function compared to our function g of x? Well, we are subtracting 3 inside of the parent function. Again, when you subtract a quantity inside of the parent function, that's going to generate a horizontal shift. To figure out what our horizontal shift is, we need to identify this constant b. Remember, it comes in the form of x minus b, which means in this particular case, our b value is going to be 3. That would give us x minus 3 inside of the parent function. Because b is positive 3, this means that our graph is going to have a horizontal shift to the right 3 units. When we go to sketch our graph, always a good idea to start off with the shape of the parent function. All right, f of x equals the absolute value of x. We get this nice V shape. And what is going to happen to every single point on the parent function? Well, you guessed it, every single point on the parent function is going to get shifted to the right 3 units. Moving that V to the right 3 units. Notice that this point that was at the origin 0, 0 now moves to the right to 3, 0. Those are our horizontal shifts. Now, we also have vertical scalings. These are known as vertical stretches and vertical shrinks. Given a parent function f of x, the function g of x equals c times f of x has a vertical stretch if the absolute value of c is greater than 1, or a vertical shrink if the absolute value of c is between 0 and 1. Notice that the constant c is a constant multiple. That means it's a number and it's connected to our function f of x by multiplication. It is a constant multiple in front of the parent function. Identifying any constant multiple in front of the parent function will allow us to determine any vertical scaling. For example, identify the parent and sketch any describe any transformations and sketch the graph. G of x is equal to 3x squared. Well, what type of function is this? It's a quadratic. What's the most simple form of a quadratic function? F of x is equal to x squared. There we have our parent function. What's different from our parent function to get to our function g? Well, we have a 3 constant multiple in front of the parent function. That's 3 times f of x. So that means that our constant multiple c is equal to 3. Because the absolute value of c is greater than 1, that means that we have a vertical stretch by a factor of 3. Okay, let's now think about the graph. One thing to recognize is that these vertical scalings impact the y values, okay, the y coordinates of every single point. So here I have my graph of my parent function. This is the graph y equals x squared. What we are going to do is we are going to take the y coordinate of every single point on this graph and multiply it by 3. Okay? Vertical scalings affect the y coordinates. We're going to multiply them by whatever c is. In this case, c is equal to 3. That means that this y coordinate that was at y equals 1 is now going to move up to y equals 3. This y coordinate, which was y equals 4, I multiply 4 times 3, that's going to bring me up to y equals 12. Similarly, I had the y coordinate of 9. Well, what's 9 times 3? 9 times 3 is 27. That's going to move that point up to here. Okay, here I had a y coordinate of 16. What's 16 times 3? That's going to bring me up to 48. Okay, every single y coordinate on this graph is going to get multiplied by 3. That will give me the sketch of g of x. Notice here, the y coordinate is 0. If I multiply that by 3, I still get 0. So the vertex does not actually move. All right? Here in blue, I have the graph of g of x. G of x is equal to 3 times x squared. This is a vertical stretch by a factor of 3. Again, vertical scalings impact the y values. Take the y values of your parent function and multiply them by the constant c. Let's look at another one here. Identify the parent and any transformations. Sketch the graph. Here I have g of x is equal to 1/2 times the absolute value of x. What type of function are we dealing with? This is an absolute value function. f of x is equal to the absolute value of x. What's different in our function g? Well, we have a constant multiple of 1/2. This is 1/2 times our parent function f of x. Well, identifying the constant multiple in front of the parent function will tell us about our vertical scaling. In this case, c is equal to 1/2. Because the absolute value of c is between 0 and 1, this is going to be a vertical shrink by a factor of 1/2. Now, as we said, vertical scalings impact the y-coordinates. What we need to do is we take our parent function. Here's our parent function, y equals the absolute value of x. And we are going to take the y-coordinates of every single one of the points on this graph, and we are going to multiply it by 1/2. In other words, let's look at this point right here. This point that was at 2, 2. The y-coordinate was 2. If I multiply that by 1/2, that brings me down to 1. Let's look at this ordered pair here. This was 4, 4. I multiply the y-coordinate 4 by 1/2. That brings me down to 2. Okay, here we had the ordered pair 6, 6 on the parent function. I multiply the y-coordinate by 1/2. 6 times 1/2 is going to bring me down to 3. So again, every single y-coordinate on the graph of my parent function gets multiplied by this value of c. That will give me the graph of g of x. This is g of x is equal to 1/2 times the absolute value of x. So those are your vertical scalings. Notice you have vertical stretches and vertical shrinks. Vertical stretches will pull your y values away from the x-axis. Vertical shrinks will pull the y values of the parent function towards the x-axis. Now, if you had to guess, we also have horizontal scalings. And just like with our vertical scalings, we have horizontal stretches and horizontal shrinks. Given a parent function f of x, the function g of x equals f of a times x has a horizontal shrink if the absolute value of a is greater than 1, or a horizontal stretch if the absolute value of a is greater than 0 and less than 1. Notice that a is a constant multiple. Again, it's a number connected by multiplication. However, in this case, that constant multiple is located inside of the parent function. All right, so being able to identify the constant a, the constant multiple inside of the parent function, will give us our horizontal scaling. For example, g of x is equal to the square root of 4x. Well, what type of function are we dealing with? This is a square root function. Our parent function is f of x is equal to the square root of x. What's different from our parent function? Well, we have this 4 constant multiple inside of the parent function. Constant multiple inside of the parent function. We need to identify the constant a. In this case, a is equal to 4. That's the constant multiple that comes in front of the x. A times x. A times x. Because the absolute value of a is greater than 1, or in this category right here, this is a horizontal shrink by a factor of 4. Now, how is this going to impact our graph? Well, here I have the graph of the parent function, y equals the square root of x. Again, this is our swim move. Horizontal scalings are going to affect the x-coordinates. I'll say that one more time. Horizontal scalings are going to affect the x-coordinates. What we can do is take every single x-coordinate on this graph, and we are going to divide it. Notice I said divide this time. Divide it by a. So, for example, here I had the x-coordinate x equals 4, right? This corresponds to the point 4, 2. Well, if I take the x-coordinate 4 and I divide it by a, 4 divided by 4 gives me 1. This point is going to shift, get compressed towards the y-axis, right? We are shrinking it horizontally, and my new ordered pair will be 1 comma 2. Similarly, here I had the x-coordinate of 8. Well, if I take 8 and I divide it by 4, that's going to bring me to 2. All right, that point on the graph of our parent function is going to get shrunken towards the y-axis and brought to 2. Okay, all of our x-coordinates that we see on our parent function are going to get divided by a. So, again, take a look. Notice this one that was at x equals 1. That's going to move to x equals 1/4. This one that was at x equals 4. That's going to move to x equals 1 because 4 divided by 4 is 1. This this x-coordinate that was at x equals 8. 8 divided by 4 brings me to x equals 2. This x-coordinate that was at 12. 12 divided by 4 brings me to x equals 3. And one more here, we had x equals 16 on the graph. 16 divided by 4 gives me 4. That's going to move to x equals 4. Notice that the y-coordinates are not impacted. Horizontal scalings affect the x-coordinates. Take the x-coordinate of the parent function and divide it by a. This gives us our horizontal shrink, in this case, by a factor of 4. Now we have our function g of x equals the square root of 4x. Identify the parent and any transformations. Sketch the graph. G of x is equal to the quantity 1/3 x cubed. Well, what type of function are we dealing with? Again, always a good idea to identify the parent function. This is a cubic function, and the most simple form of a cubic function is f of x is equal to x cubed. What's different from the parent function? Well, inside of the parent function, notice it's inside of the parentheses, I have a constant multiple of 1/3 connected to this x. I have some constant multiple a times x. Well, what's the constant multiple that's in front of the x? In this case, a is equal to 1/3. Because the absolute value of a is between 0 and 1, this is going to generate a horizontal stretch. A horizontal stretch by a factor of 1/3. So here we have our parent function, f of x equals x cubed. As we said before, horizontal scalings impact the x-coordinates of our parent function. What we are going to do is we are going to take every single x-coordinate on our parent function, and we are going to divide it by a. Now notice, dividing by 1/3, that's the exact same thing as multiplying by 3, and that is why our values are going to get stretched out. Okay, our x-coordinates are getting multiplied by 3. Again, divide by a to get your transformation. Dividing by 1/3 is the same as multiplying by 3. So let's take a look. This was an x-coordinate of 2. What's 2 times 3? That's going to come out to 6. This point right here corresponded to an x value of 3. What's 3 times 3? That brings me out to 9. This point right here corresponded to an x value of 4. What's 4 times 3? That brings me to 12. And I could do the exact same things over here on the left-hand side. Notice an x-coordinate of -2. Dividing by 1/3 or multiplying by 3 brings me to -6. An x-coordinate of -3. I divide by 1/3 or multiply by 3. That brings me to -9. So on and so forth. Every single x-coordinate of every point on this graph is going to get divided by 1/3 or multiplied by 3. This brings us to the graph of g of x is equal to 1/3 x cubed. All right, we have 2 more transformations to talk about. Reflections. Given a parent function f of x, the function g of x equals c times f of x has a reflection in the x-axis if c is negative. Now, you might recall, c had another job as well. This constant multiple in front of the parent function also determined our vertical stretches and vertical shrinks. Well, if c is negative, that causes a reflection in the x-axis. Example, identify the parent and any transformations, sketch the graph. Here we have g of x is equal to negative x squared. What's the parent function? Well, f of x is equal to x squared, right? It is a quadratic. What's different about our function g? We have negative 1 times f of x, negative 1 times the parent function, negative 1 times x squared. That means that our constant multiple in front of the parent function is negative. When our constant multiple in front of the parent function is negative, that is going to generate a reflection in the x-axis. Here we have the graph of our parent function. F of x is equal to x squared. How are we going to get to the function g of x? We are going to take that graph and reflect it over the x-axis. There's my x-axis. Flip it on over. That gives us the graph of g. G of x is equal to negative x squared. Our last transformation here, given a parent function f of x, the function g of x is equal to f of a times x has a reflection in the y-axis if a is negative. Now, a is a constant multiple that is inside of the parent function. As we discussed earlier, this a constant multiple also controls our horizontal stretches and shrinks. However, in this case, if a is negative, that means that we have a reflection in the y-axis. For example, here we have the function g of x is equal to the square root of negative x. What's our parent function? What type of function are we dealing with? Well, this is a square root function. We have f of x is equal to the square root of x. That is our most simple form of a square root function. What's different from our parent function to get to the function g? Well, I have a constant multiple inside of the parent function in front of this x. I have some constant multiple a times x inside of the parent function. What's a in this case? Well, a would be negative 1. And if a is negative, that means we have a reflection in the y-axis. So here is the graph of our parent function. F of x equals the square root of x. To get to our function g of x, we are going to take that graph and reflect it right over the y-axis. And here we have the graph of g of x is equal to the square root of negative x. So here is a quick summary of all of your transformations. Given the real numbers a, b, c, and d, and the function f, the graph of y equals c times f of a times the quantity x minus b, plus d is obtained from the graph of y equals f of x in the following steps. Again, you will want to be able to identify each one of these constants, a, b, c, and d. A controls our horizontal scalings, all right? Those are your horizontal stretches and horizontal shrinks. B controls your horizontal shifts. That's when we subtract a constant inside of the parent function. A was a constant multiple inside of the parent function. Our vertical scalings, our vertical stretches and vertical shrinks, all right, are generated by our constant C. Identify what the constant C is. That's our constant multiple in front of the parent function to determine your vertical scalings. And finally, we had our vertical shifts. The vertical shift is determined by this constant d that is added outside of the parent function. We will have a vertical shift of d units. And as we just discussed, if c, the constant multiple c, that's the constant multiple in front of the parent function, is negative, there is a reflection in the x-axis. And if a is negative, that's the constant multiple inside of the parent function. If a is negative, there is a reflection in the y-axis. So when you sketch your graphs, pay particular attention to this general form, right? Y equals c times f of a times the quantity x minus b plus d. From here, identify the constants a, b, c, and d, and that will tell you the transformations that you have. Now, when you go to sketch these graphs, follow this particular order. 1, do your scalings first, okay? Complete your vertical stretches, vertical shrinks, horizontal stretches, and horizontal shrinks first. After you do your scalings, then reflect your graph. Then do your reflections over the x-axis and or y-axis. And finally, thirdly, what number should that be? That should not be a 2. That should be a 3. Thirdly, do your shifts. Shift the graph up, down, left, right as necessary. Okay, following that order will give you the correct graph. When you guys go to sketch your graphs, I'm not looking for your sketches to be perfect, okay? So don't worry about them being perfect. If you have the general shape, that's fine. And again, I'm going to ask you specifically to identify the transformations. So it's very, very important that you are just writing those transformations down. Identify the transformations. Make sure your sketch looks decent. It should have the general shape. And if you can plot 2 or 3 points on the graph, you're going to be in good shape. Hopefully this made some sense. We'll get into some more example problems coming up.